Welcome to Maths with EJD. In this video, I'll be talking about supply chain optimization with linear programming. Of course, we've been talking about linear programming all this while. I just want to show how particularly applicable it is to supply chain optimization. And since I've explained the simplex method and all of those methods, so what I'll be doing um, in this video would just be to show how we formulate the problem, and then I'll just go ahead straight to use Python to solve the problem, since I've already established how to do the simplex method. So as a way of reminder, we know that linear programming, which is LP for short, is a mathematical technique used for optimization, where we aim to maximize or minimize an objective. So the objective could include things like cost, profit, or even time. And all that will be subject to a set of constraints. Okay. Now, in the context of supply chain, in the context of supply chain optimization, linear programming can be used to determine the most efficient way to allocate resources, such as material, time, or transportation, while minimizing costs or maximizing efficiency. Okay, so that's how that is. Let's look at an example. Let's look at a problem setup in supply chain. Consider a company that needs to supply products from two warehouses to 3 stores. Okay, the goal is to minimize the total transportation cost, to minimize the total transportation cost, while ensuring that demand at each store is met, and that the supply at each warehouse is not exceeded. Okay. Now, the table below just represent we can have a table to represent that reality. So imagine that we have warehouse, warehouse, W1, W2, and then we have okay, warehouse is down here, and we have store the other way. Um, so let's say this is store one and store two and store three. So something like this. And we also have this is the demand side of things. So the stores will demand while the warehouses will supply. So this is the supply side of things now. So warehouse one can supply 100. Okay, I guess I want to change the color for this. So warehouse one can supply 100 items like that. And then warehouse two can supply 150. Then on the other hand, we have for the demand now, where store one rather, store one demands 80, store two demands 120, while store three demands 50. And then we have the costs. We have the costs. So now the costs are 4, 6, 8. You can take that to be in dollars, for instance. So the cost to move one unit of good, okay. The cost to move one product is $4 from warehouse one to store one, $6 from warehouse one to store two, $8 from warehouse one to store three. This should be store three. Okay, this is store three. Okay, then it is from warehouse two to store one is $5. Warehouse two to store one is $7. Warehouse two to store three is $6. So that's the kind of setup we have for this. Okay, so like I said, right, we can say where the values in the table represent the transportation costs, the transportation costs per unit from each warehouse, from each warehouse to each store, say in dollars. Then we also have the supply capacities. The supply capacities at warehouse one and warehouse two are 100 and 150 units respectively, as we see in the table. Then lastly, we have the demand. The demand at stores S1, S2, S3 are 80, 120, 150 respectively. Okay. So this is more like the problem. So the table simply summarizes what this problem looks like, right? So the next thing we want to do is to find a way of dealing with that. So we have to determine what our decision variables are. So what will be our decision variables in this case? So here we can just say let Xij represent, let Xij represent the amount of product That's or number of products, right? The amount of products transported, transported from warehouse, from warehouse I to store J, warehouse I to store J. So where I will be 1 and 2, representing representing warehouse 1, warehouse 1, representing warehouse 1 and warehouse 2. And J now, J, which is 1, 2, 3, represent the stores. So representing S1, S2, S3, like that. Okay, I mean, now that we have the decision variables, right, we can just we can go straight. I'll just go straight and talk about um the problem. So we can have the linear programming formulation. Okay, I guess it's better to use this now. Linear programming formulation. So we already know the deal is to minimize the transportation cost, right? So it means we have to minimize, minimize Z equals now. So, if you look at this now, this can be like, this is, so the first one here, you have X11 because warehouse 1 to store 1. That can be X11. This is X12, warehouse 1 to store 2, X13. This can be X21, X22, X23. So those are the 6 variables we are going to have. So in this case now, it means that we want to minimize Z equals, want to minimize Z equals 4x11 plus 6x12 plus 8x13 plus 5x21 plus 7x22 plus 6x23. So those are the 6 things we have now. So minimize 4x11 plus 6x12 plus 8x13 plus 5x21 plus 7x22 plus 6x23. So that's basically what we have coming from the table. So this is our objective function, right? So this whole thing is okay, I can just say this is objective function, right? So next we have different layers of constraints. First of all, we can talk about the supply constraints. Supply constraints. So for the supply constraint, right? So you see that the supply is this way. So it means we're going to have so we can have a possibility of X11 plus X12 plus X13 supplies from warehouse 1 to the 3 different warehouses respectively. So we have basically 2 different supply constraints. So the supply constraint now will just be X11 plus X12 plus X13 less than or equal to 100, and that is for warehouse 1. Okay, 100, sorry, that's 100. So, and that is for warehouse 1. For warehouse 2, to be X21 plus X22 plus X23 less than or equal to 150, because warehouse 2 can only supply a maximum of 150. So those will be the supply constraints. And then we have the demand constraints also. There are also constraints on the demand. So we have demand constraints. So for the demand constraints, you take it downwards, right? So this is how supply constraint goes. Okay, guess I should do this. This is how supply constraint goes. But the demand constraints will have to come down, right? Will have to be say this and this and this and this for each column, right? So we have for the demand constraint, for the demand constraint, we have what you see there. Um, so that means for the demand constraints, we have X11. Okay, this is changed now. We have X11 plus X21 is equal to 80. So, so if you combine what the stores are requiring, it has to be 80. Then the other one, so the amount of product shipped to each store must meet the store's demand, right? The amount of product shipped from each warehouse cannot exceed the supply of the warehouse. That was when we dealt with the warehouse. So now here we have X12 plus X22 equals 120. And of course, this is store one, this is store two. And lastly, we have X13 plus X23, and that is equal to 50 for store three, like that. So of course, there'll be non-negativity constraints, right? So we have non-negativity constraints as usual. Non-negativity constraint, because we cannot have negative number of products, right? So non-negativity constraint, that would just be that all the xij's are greater than or equal to 0, where xij is greater than or equal to 0 for every I, comma j. So another way of saying that would have been, of course, this simply means the same as this, that x11, x12, x13, x21, x22, and x23, they are all greater than or equal to 0. That's basically what that means. Okay. So with that, we have the problem set up. So you can now use simplex method to solve all of this. You can use simplex method. Yeah, basically you cannot use graphical method because once you have here we have 6 decision variables. So graphical method can only handle 2. So simplex method can take care of this, and maybe for some more advanced methods. But I mean, for the purpose of this, I'm just going to show you the solution using Python, so that we save time. So let me just go. So if you look at this now, I used Python. I used the, 2 libraries. I used PuLP in Python, and I also use scipy.optimize. That's .linprog. Linprog is linear programming, and scipy.optimize. So look at the PuLP, right? Okay, for the PuLP, right, we have 40 lines of code, and for this we have just 33. So it all depends on how the setup looks. So here now, uh, so you can see the problem is defined in line 4. Of course, we have to import PuLP in line 1, and then line 7 to 12 is where we define the decision variables amount to be transported. So x11 up to x11, x12, x13, x21, x22, x23, like that, and all their. So it is bounded below by 0 because it cannot be negative, and then it goes up. So W1 to S1 and things like that, just like you saw. And one beauty about PuLP is that you can declare the problem directly the way it is. So this is the objective function, which is the total transportation cost. Then for the supply, W1 supply, W2 supply, and all the demands, you just define all that. And the actual solving is happening in line 27. And then the rest is just to output the results. Okay. And in one blow, you just get the answers. So you see that S1, so transportation cost, the number of units you need to transport from W1 to S1 is 0 units, W1 to S2 is 100 units, W1 to S3 is 0 units, W1 to uh W1 to S1 is 80 units, W2 to S2 is 20 units, and W2 to S3 is 50 units. So total transportation cost is 1440. Okay. Okay, I'm still going to go back to that page to clarify this better. So here we have the using linprog now. So you also define this one. So in PuLP, you define the problem directly, but here you use the coefficients of the matrices. So 4, 6, 8, 5, 7, 6 are the coefficients of the objective function, just like all this 4, 6, 8, blah blah. And then for the supply side, right, we have 11111 all through, you know. So for the supply side, right, we have 111 for the that's for 111 to 13. Then the rest will be zero. And for the supply constraint, the second one, that'll be x, that's x21, x22, x23. So that's 0000111. And then the right hand side is 150, 100 and 150. Then for the coefficient of the inequality constraints too. So these are the inequality constraints. For the equality constraints, we also have those things like that. Because here now, for the supply side, we only have X11, X12. We have X11, X21. So if you are defining that, right? So X11 has something, X120, X130, then X21 is 1, and all of that. So, and then you have the right answer, which is 81, 20, 50. So the bounds, of course, six of them is from 0 upwards, so it's non-negative. And then this is implemented using the simplex method. So if you run it again, you also get the same result: 0, 100, 0, 80, 20, 50. 0, just like what you got here: 0, 100, 0, 80, 20, 50. And the total transportation cost is $1,440. So I'm going to take the answers back and, 0, 100, 0, 80, 20, 50. Okay, let's take that back and finish things up. Okay. Um, okay. We can talk now that using Python, right? Okay. Using PuLP and or linprog. Either one is fine. You don't have to use both, but I just use both to show uh that. So using PuLP or scipy.optimize.linprog, linprog, linprog, that's linear programming in Python. The optimal solution, the optimal solution is given as x11 equals 0, x12 equals 100, x13 equals 0 again. Then x21 is 80, x22 is 20, and x23 is 50. Okay. And as a result of that, right, if you put all of that into the objective function, you know, you get 1440. So if you look at the objective function again, what is it now? Yeah, the objective function is 4x11. Okay. If you put all this into the objective function, which is, so the objective function, from the objective function, which is given as z equals 4x11 plus 6x12 plus 8x13 plus 5x21 plus 7x22 plus 6x23. Okay, 6x23. So, we have z now to be 4 times 0 plus 6 times 100 plus 8 times 0 again plus 5 times 80 plus 7 times 20 plus 6 times 50. Okay, so that z is 0 plus 600 plus 0 plus 400 plus 140 plus 300. Yep. Yes, 300. So z now is 1,440, right? 1,440. So that's what that is, 1,440. So z is 1,440. 40. Okay. So how do you conclude that? So the conclusion is that um is that to optimize, okay, optimal transportation. Okay, how do I put this now? I'm looking for a nice way of explaining this. Okay, the let me just put it this way: to spend the least cost, to spend the least costs of to spend the least costs of $1,440. Ship ship um zero products, ship zero products, ship zero products from warehouse one to store one. Okay. 100 products from warehouse one to store two. Then ship zero products again, zero products from warehouse one to store three. Okay. Then ship 80 products from warehouse two to store one. Then ship 20 products from warehouse two to store two. And 50 products, ship 50 products from warehouse two to store three. And that is the optimal solution in this case. Now, for transportation problem, right, we have a couple of methods that can. Oh, okay, sorry. This is oh, we are not. This is okay. We are minimizing transportation costs definitely, but this is a supply chain problem. But in the next video, I'll be talking about transportation problem. That corresponds with this. Okay, this is supply chain, but it's still talking about transportation. Of course, transportation is supply chain, but there are some set of problems called transportation problem, which we are going to see. You know some in the subsequent videos. So if you have not subscribed to this channel, do that right away and hit the notification bell so you can always get alerted each time a new video is released. And also comment, let me know if you want me to teach a topic or solve a problem. Also like and share so that more people can have access to this great learning. Till I come your way again, have a very nice time. Bye.